Alright, here we're going to be talking about the graphs of exponential functions, right? So I just did another video where I talked about the definition of an exponential function, just basically what it looks like, and then also evaluating an exponential function. Here we're going to talk about the other side of it, is what does an exponential function look like when we actually graph it, right? So the two videos I'm doing here on exponential functions kind of go together. So if you didn't watch the other one, you should check that other one out to get kind of the whole picture of what's going on with exponential functions. Alright, so anyway, an exponential function, as we know from that other video, has the form f of x equals a to the x power, where a is greater than 0, but a is not equal to 1. Alright, I kind of explained why that is in that other video. So we have a base number, some positive number other than 1, raised to the x power. Remember, that variable, the x in the exponent, is what makes it an exponential function. Alright, so when you graph an exponential function, the domain is all real numbers, from negative infinity to positive infinity. Right? When I have a number, so let's say I have 3 raised to the x power, I can plug in any number for x. I can plug in positive numbers, negative numbers, big numbers, small numbers, fractions, decimals, or rational numbers, irrational numbers. It doesn't matter, and I can always raise that base number to that power and get a result. All right, so my domain is all real numbers, which means my graph is going to stretch to the left and to the right in both directions forever. All right. Now my range, though, my range is not all real numbers for an exponential function. My range for this basic type of exponential function is from y equals 0 up to infinity, right? And notice the y equals 0 is not included. It has that parentheses there, which means that that endpoint is not included, right? So the range, the y values, or the output values that I get from an exponential function go from, very, very small positive numbers, right, just bigger than 0, and then every other positive number all the way up to infinity. Right, so the range of an exponential function is basically all positive y values, but not y equals 0 and not any negative y values. Right? If you think about why that would be, think about an exponential expression. Right? If I have a positive number, again, let's just take 3 as a basic number to use. If I have 3 raised to a power, well, if I use a negative exponent, is that going to give me a negative result? It's not, right? Because if you recall the rules of exponents, which if you don't recall them, you should check out some of the videos I did on the laws of exponents. But if you raise a power to a negative number, you take the reciprocal of that base number, right? So like 3 to the negative 1 power, that's not negative 3, it's 1 over 3, it's 1/3, right? So when I plug in, negative x values, I just get basically fractions, and I get smaller and smaller numbers, so I never actually get a negative result, right? If I have a positive number raised to a power, that's never going to give me a negative result. Or a 0 result is always going to give me a positive number. All right? So that's my domain and range. Another feature of the graphs of exponential functions is that they have horizontal asymptotes at y equals 0, which is the x-axis. Right? So I talked about horizontal asymptotes on the videos that I did on rational functions. Remember, a horizontal asymptote is a horizontal line that the graph approaches either on the right side as it approaches positive infinity, or on the left side as it approaches negative infinity. Way out to the right and way out to the left, for exponential functions, the graph is going to approach y equals 0. All right, now these are the rules and the attributes of the graphs for the basic type of exponential function, a to the x power. Now, you can also apply transformations to graphs of exponential functions, and in other videos I did, I talked about transformations of graphs of some other types of functions, but those same rules apply to exponential functions. So I could have a graph that looks like this, but if I have transformations, like the graph could be moved up or moved down or stretched or flipped over, so any of those transformations could happen. So these things here, the range and the horizontal asymptote, could change if you have more than just the basic a to the x power. Right? If I have f of x equals 3 to the x power plus 2, well, that's going to change where I have my horizontal asymptote. It's going to raise everything up 2 units. Or if I have a negative 3 to the x power, that negative is going to flip everything over, and now my range is from negative infinity to 0 instead of 0 to infinity. Right? And at the end of this video, I'll do some examples where we apply transformations to these graphs. But I just want to point out to you that the graph is not always going to look exactly like this. Right, this is just the graph of the basic type of exponential function, just a number raised to the x power. But if you start adding, subtracting, multiplying things in there, it can change the way the picture looks. All right, so this is the graph of your basic exponential function when your base number a is bigger than 1. Right, so 2 to the x power, 3 to the x power, 1.3 to the x power. Those graphs are going to look something like this. Right, they're always increasing. Right, so they have the y-intercept at 0, 1. Now again, that can change if we do transformations to the graph, but if you think about it, if I just have a number raised to the x power, if I plug in x equals 0, then I have a number raised to the 0 power, and anything raised to the 0 power other than 0 equals 1. Right? 3 to the 0 power equals 1. 5 to the 0 power equals 1. Right? So my my y-intercept is always going to be 1. All right? And notice here, out on the left side, as x approaches negative infinity, my graph keeps getting closer and closer to that horizontal asymptote at y equals 0, which is the x-axis. Right? So if I have a positive number, again, like 3 to the x power, if I plug in really big negative numbers for the exponents, if I plug in like 3 to the negative 1 million power, well, that's 1 over 3 to the 1 millionth power, which is 1 over a really huge number, which is really close to 0. Right? So as we get bigger and bigger negative numbers, the graph gets smaller, or the output values get smaller and smaller and closer to 0, but again, they'll never actually reach 0. Right? There's no number that I could plug in for x that will make an exponential function equal 0, or that will give you a negative result. Right? So this line, or this graph here of the exponential function, never touches that horizontal asymptote and never crosses over to the other side. Right? Over here is what the graph of an exponential function looks like when my a value is less than 1. So that would be like if I had 1/2 to the x power, or 0.03 to the x power. All right, those graphs are going to look like this, which is kind of just the mirror image of this graph over here. If I take this one and just kind of flip it over that way, it's the same basic graph. Now, what that base number is will change, like how steep the graph is and how quickly it rises, but they all have the same basic shape. All right, so once again, we have a y-intercept at 0, 1, because, again, any number raised to the 0 power, when I plug in x equals 0, it's going to equal 1. This one, though, has that horizontal asymptote on the right side. Right? As I move way off to the right, as x approaches infinity, if my base number is less than 1, my graph is going to approach 0. Right? So that's my horizontal asymptote there. All right, so those are the two basic shapes of exponential functions, or the graphs of exponential functions. They are important to know, and it's important to know when you're going to get one or the other. Right? If your base number is bigger than 1, you have a function that's always increasing. If your base number is less than 1, you have a function that's always decreasing. Right? Think about it. If your base number is like 1/2, if you keep multiplying 1/2 times itself over and over again, well, 1/2 times 1/2 is 1/4. It gets smaller, right? 1/4 times 1/2 is 1/8. It gets smaller again. So when that base number is less than 1, when you keep multiplying it, remember, exponentials are repeated multiplication. When you keep multiplying it, you keep getting smaller and smaller results. So as this graph goes off towards infinity, as x goes towards infinity, the graph goes down towards 0, because you keep getting smaller and smaller fractions as you keep multiplying it. Whereas if your base is bigger than 1, if I take 3 and keep multiplying 3 times itself over and over again, well, the numbers just keep getting bigger and bigger, and they kind of skyrocket, and that graph goes off towards infinity. Right? But both graphs stretch in both directions forever, right? From x's negative infinity out towards x's positive infinity. All right, so those are the basics of the graphs of exponential functions. I'm going to pause the recording, erase this stuff, and put up a picture of what we call the family of exponential functions, just so you can see how they relate to each other, and then we'll also do an example where we graph some. All right, so I put up here some graphs of what we call the family of exponential functions, just so you can kind of compare what the different graphs look like depending on how that base number changes. All right, so the first one I did up here is the one in blue, which is y equals 2 to the x power. Notice for 2 to the x power, on the right side for positive x values, that's lower than the other bases, which are 3 and 5. Right? So I graphed basically 3 functions where the base was bigger than 1. 2 to the x, 3 to the x, 5 to the x. Notice the smaller that base number is, the less steeply the graph rises for positive x values. Right? So the 2 is like smaller, the 3 is a little bit taller than that, the 5 is much more steep. Right? Which makes sense because remember, exponentials are repeated multiplication. So if I multiply 5 times 5 times 5, that's going to grow a lot faster than if I multiply 2 times 2 times 2. Right? The numbers still grow quickly, but not as quickly as multiplying a bigger base over and over again. Right? So the bigger your base number is on the right side for positive x values, the more quickly the graph is going to grow. But on the other side, for negative x values, the smaller base is actually higher, and the bigger base is actually lower. And again, because negative exponents represent reciprocals, right? So if I do 5 times 5 times 5, that's 125. But if I do 5 to the negative third power, that's 1 over 125, right? Which is a very small fraction. Whereas if I do 2 to the third power, 2 times 2 times 2 is only 8. Right? So over here, that's a lot lower than 5 to the third power, which is 125. But when I do 2 to the negative third power, that would be 1/8, which is a lot bigger number than 1 over 125, right? Which is why the smaller base on the left side for negative x values is actually higher, because you're still getting small numbers, you're getting small fractions, but not as small as if you do a higher base to that same negative power. Right? So I hope that makes sense as far as why the graphs behave the way they do. And notice they all have that same y-intercept at 1, right? Because no matter what your base is, if you raise it to the 0 power, it equals 1, right? So all those graphs meet up at the point 0, 1, and then they all just spread their separate ways, and they never actually meet up again. Out here, all of these approach 0 as x approaches negative infinity, but they'll never intersect again. They'll always stay, a little bit apart from each other all the way out towards negative infinity, right? And same deal on the other side. The ones going the other way, the decreasing functions here, are the ones where we have a base number that's less than 1, and what I did is just the reciprocal. So the blue one over here is 2 to the x power. The blue one on this side is 1/2 to the x power, right? 1/2 being the reciprocal of 2, 1/3 to the x, the reciprocal of 3, and 1/5 the reciprocal of 5. And notice that each one of those, and if I had drawn this perfectly, you would maybe see it a little more clearly, but each one of these, that's the reciprocal, is just the mirror image of the one on the other side. Right, so if I take the graph of y equals 2 to the x, and I flip it over the y-axis, do that horizontal reflection, I get the graph of 1/2 to the x power. Right, the graph of 1/3 to the x power is the graph of 3 to the x just flipped over. Right, 1/5 to the x is the reflection of 5 to the x. Right, so the reciprocal graphs are the mirror images or the reflections of the graphs of the base number that's bigger than 1. Right, if you think about it, if I were to do, or let me just take 1/2 as the example here. Well, actually, let me take 1/5 so I can keep it all color-coded. Right, if I have 1/5 raised to the x power, well, 1/5 is 5 to the negative 1 raised to the x power. Right, then that negative 1 exponent means the reciprocal of 5, which is 1/5. And then when I have a power to a power, I can multiply them, so negative 1 times x is negative x. Right, so 1/5 to the x power is the same thing as 5 to the negative x power. Right, so having a base less than 1 is actually the same as having a base bigger than 1 raised to a negative power. Right, and if you recall, for the rules for transformations of graphs, if you've seen the videos I did on those, when I have a negative with the x, that gives you that reflection across the y-axis. Right, which is taking this graph of 5 to the x, and if I do 5 to the negative x, I flip it this way. But as we can see, 5 to the negative x is the same as 1/5 to the x. Right, so again, just trying to tie different ideas together here. The graphs of these exponential functions tie in directly with the laws of exponents, where if I have 1/5, that's the same as a negative 1 power. It ties directly in with the rules of the transformations of functions with the reflections. When I have a negative on that x, it reflects it in the y-axis. Again, all these things tie together, right? All these different areas of math where you would think, well, the graphs of exponential functions, that has nothing to do with what we talked about earlier with transformations, but it does, right? It's very much related, as we can see here, right? So those are, the family of exponential functions. Again, just having an idea, they all have the same basic shape. Like all the ones where the base is bigger than 1 have the same basic shape, but the bigger that base is, the more steeply the graph grows on the right side. All right, I'm going to pause this and then real quick put up some examples, or maybe just one example of doing transformations of graphs and seeing how those work. All right, so I put up here the graph of a parent function, y equals 2 to the x power, which is the one that's up here in red. Right, so that's the basic graph of 2 to the x, and then 3 graphs that involve transformations of the graph of that parent function. So if you haven't seen the videos that I did on the rules for transformations, I did a whole bunch of them for all the different rules. You might want to check those out. Those rules apply not just to the functions that we talked about on those videos, but to any type of function. Right, the exponential functions here, logarithmic functions, trigonometric functions when we get to those. Any function follows those same rules for transformation. So if this red one is the graph of 2 to the x, to graph 1 plus 2 to the x, well, that plus 1 is a vertical shift up 1. So I take that red graph, I move every point up 1, including that horizontal asymptote, now becomes y equals 1, and then that's the graph of 1 plus 2 to the x. Every point just moved up 1 unit. Right, y equals 2 to the x minus 1. Right, when I subtract that 1 from the x inside the parent function in the exponent, I move everything to the right 1 unit. Right, so that's the graph of that one. Y equals negative 2 to the x. Well, that negative in front is the reflection over the x-axis. It flips it all over, so now it's going down here. Right, so just a couple examples of transformations of graphs. Again, if you haven't seen the videos I did on those, you might want to check those out.